Hey everyone, welcome to the sixth video in our series on the reactions of chapter 8. Okay, so the last video we just talked about addition of halogens. In this video, we're going to be talking about a variation on addition of halogens, which is formation of halohydrin. So formation of halohydrin. Okay. So, in formation of halohydrin, again, this adds X and H2O, right? And I shouldn't say H2O. It adds X and it adds OH across the double bond, which we'll see what that means in a second. And then, X can be chlorine, bromine, iodine, same thing as with addition of halogens, right? This one is still anti-addition, and it's Markovnikov. And it also forms the enantiomer. Okay, so I think that these are the important parts of this reaction. Okay, so you'll remember in the last video, whenever we talked about addition of halogens, we had Cl2, Br2, I2, whatever, over CCl4. In this case, we're going to have Cl2, I2, Br2 over water. Okay, so if we have it over water, then we get a similar product. Okay, so we get a alcohol here, and then we get a chlorine here. Okay, so let me explain this a little bit. Let me write this correctly first before I explain anything, though. So these will be trans, and I did not write them as trans. Okay, they're anti from each other, right? Because this is anti-addition, so the OH and the Cl are going to be opposite each other. And so in the last one, we added a chlorine on both carbons, right, in the double bond. But in this case, we're not adding the chlorine on both carbons. We're adding the chlorine on one, and then we add the OH on the more substituted carbon. Okay, so you'll notice OH went on this carbon and not on this carbon. There's a reason for that, because OH only goes on the more substituted carbon. Okay, so if we look at another example, this time we'll use Br2. And water. Then what happens in this one is that I get OH on more substituted, and then on less substituted, I get Br. So that's why we say it's Markovnikov, because OH is going on more substituted, and the bromine goes on the other carbon. And it's also anti because the OH and the Br are going to be opposite each other. Okay, and then we also get the enantiomer of this one as well. This one has an enantiomer also, but we won't worry about that one. That was kind of a strange example. Because only one carbon is chiral, only this one's chiral, so we won't worry about drawing the enantiomer for this one. But this one has an enantiomer. Both of these carbons are chiral, so that's really all that there is to this one. I think that it would be good to do the mechanism for it, though. This is an important mechanism for sure, so I would definitely study this mechanism. Okay, so if we start off with this, then, and let me be consistent and use Cl here. So the first step is the same as the last reaction. So it attacks and it also gets attacked, the double bond. and then chlorine leaves. So then we make the ring structure. Okay. So we make this, right? If you remember this from the last video, we make the ring. And so after we make this ring structure, in the last video, this chlorine came in and attacked, right? But my solvent is water. So there's going to be a lot of water floating around in the reaction mixture. So that means that the chances that water comes and attacks are going to be much higher. And so here's the important thing to remember about this mechanism. Water will always attack the more substituted carbon. So this carbon is more substituted, so it attacks there every single time. Okay, it will always attack there. That's why this is Markov-Nikov, and that's why we were getting the OH on more substituted on both of these reactions. Okay, so definitely, definitely, definitely remember that. And then, so I get this. I get my OH here, but it needs to be deprotonated. I still have the methyl. And then I have chlorine here, right? So then water is going to come in. There's not a plus on water, sorry. Water is going to come in and take that hydrogen off, and then I'm done. So then that gives me this product. And I'm not worrying about stereochemistry too much, except for in this one. And then I get H3O plus. Okay, so that's it for this mechanism. All right, so the only difference between this one and the addition of halogens mechanism is that in this case we use water to attack instead of another chlorine. Okay. The last thing that I want to mention is another separate example here. So instead of using water, we can use something else. So we can use alcohols instead. So let's do that second example, still with Br2, except I'm going to use an alcohol. So CH3OH. So now, instead of adding an alcohol, I add an ether. So I just add OCH3. And then I also get the enantiomer as well, right? So I get this and the enantiomer, all right? I'll move over here slightly so I can write this a little bit better. Okay, so we get that in the enantiomer. All right, so the only difference is that we add OCH3 because that's the alcohol we use. But this isn't the only alcohol we can use. We can use literally any alcohol ever. So let's do this one. And then we'll do Cl2 with CH3, CH2, OH. So now I'm using ethanol. I can use anything, right? And then my product is just going to be a OCH2, CH3 right there. And then opposite to that is a chlorine. And then we get the other one as well. Okay, so yeah, this is my these are my two products for these. Okay, so remember that with formation of halohydrin, I can use water or I can use an alcohol. Okay, and that's going to determine whether or not I get an alcohol or I get an ether. Okay, and like I said, this is an important mechanism, so I would definitely study this mechanism for sure. And yeah, I think that's all that we'll say about this one. I don't want to go too in depth on it. So Hopefully this was really helpful. And in the next video, we're going to be talking about hydrogenation, which is pretty easy for alkenes. So that's going to be a quick video. So hopefully you'll join me for that one, and I will hopefully see you there.